Hello everyone, and welcome to this new story. Tonight we're going to ask ourselves a question that has many angles and consequences. It opens many tangents too. If there had been an advanced industrial civilization in the past, the far past of our planet, millions or tens of millions of years ago, would we be able to discover it, to find its remains? In other words, what kind of traces does an industrial civilization leave behind? What objects? What buildings? What waste? What impacts on the planet? And how long before these traces disappear? This is the questioning at the heart of a hypothesis called the Silurian Hypothesis. This term, Silurian Hypothesis, appeared a few years ago, in 2018. It was the theme of a paper by two scientists, an astrophysicist called Adam Frank and a climate scientist, Gavin Schmidt. They coined or used this term after the name of a fictional species in a British sci-fi series, Doctor Who. The Silurians in this universe are a species of lizard-like humanoids, technically and scientifically advanced. So they reused this term to name what is in reality a thought experiment. What would be the ability of modern science, our ability, to detect evidence of a very ancient civilization? Not one that existed a few thousands of years ago, like archaeology studies, but millions of years ago. What could possibly remain of it? And this calls for many different approaches, many different disciplines, such as the science of materials. How long do materials last before breaking down? How long can building of stone or metal exist in different environments? Also climate science, how the signs of industrial activity could affect the climate and leave traces in geological layers, for example. Geology, too. How fast does the surface of our planet refreshes due to plate tectonics and volcanism? But also physics and chemistry. How long do artificial chemical compounds or nuclear waste really last? We are used to think about these as a long life type of waste, and they can last for thousands or even millions of years indeed. But they are not eternal neither. And these are just a few of the aspects we're going to examine tonight. Now you probably heard the term Silurian, even if you know nothing of Doctor Who. This is because this word that the writers of the show used is also the name of a very ancient geological period in the past of Earth. The Silurian period spans 23 million years, and it came after the Ordovician and before the Devonian periods, more than 400 million years ago. It is the time to which paleontologists date the appearance of vascular plants, and also when a few small arthropods became fully terrestrial. Arthropods like arachnids and myriapods. Myriapods are the group that includes centipedes, so they became terrestrial instead of living at least part-time in water. So this is to say that Silurian hypothesis does not refer to a supposed civilization during the actual Silurian period. First we saw that the name actually came from the fictional Silurians in Doctor Who, and in the show they are very ancient, but not by hundreds of millions of years. And second, the Silurian hypothesis is not about an actual civilization in the far past of Earth. It is not alternative history or pseudo-history. It is about our ability, the tools and the indicators that could make the detection of very ancient civilizations possible. And you'll see that the questions this thought experiment raises are going to take us to surprising places, like astrobiology, or our ability to detect possible extraterrestrial civilizations. We have a lot to explore, so make yourself comfortable, let the tension go in your shoulders. And if you wish to try it, I invite you to check the Lights Out Library podcast, which consists of the same stories I create for this channel, but edited and narrated by Olympia Perez, who works with me on it. She also records a Spanish version, La Biblioteca de los Sueños, and a few months ago I also started a French version, La Bibliothèque des Rêves. If you speak or learn French, that can be an option, because I speak slowly and I don't make mistakes or mispronounce anything in French. Nobody's going to learn English with me, but French you can. I'm reliable. And now, let's get started. So first, an interesting question is how long it would take for the things we make to disappear. What is the lifespan of the objects we make as an industrial society? From the most ordinary ones, like clothes or wares, to vehicles, all the way to high-performance industrial plants that use very strong materials, like carbon fiber or special steel, military tanks or the vessels of nuclear reactors, for example. For textiles, the time to decompose and eventually break down entirely to the molecular level depends highly on their types and in which environment they are placed, obviously. Natural fabrics that are biodegradable disappear the fastest. It can even be surprisingly fast. Linen from flax is the fastest. Pure linen, without other fibers or dyes, can decompose in just 2 weeks if placed in a wet soil, with ideal conditions for composting. In a dry place, it can last thousands of years. For example, the strips of linen that were used to wrap Egyptian mummies have generally been found altered, but still in a relatively good state. They had maintained their shape and cohesion, and they were made of linen. Cotton takes a few months to decompose in ideal conditions, up to 6 to 8 months in regular soil, a few years if it is dry soil, and again thousands of years in dry air. The most resistant natural fibers are wool and silk. In soil, they decompose in a few years. Now, not surprisingly, plastic-based synthetic fibers take a lot more time. Polyester, nylon, or acrylic decompose in 20 to 200 years. But that's just for the structure of the piece of fabric to disappear. What they do in nature or in landfills is fraction into tiny objects called microplastics. You heard of them. Their presence in water and soils is a potential health hazard. Microplastics are defined as particles smaller than 5 millimeters. But one particle of microplastic can still contain millions of molecules. Typically compounds like polyethylene, polystyrene, or polypropylene. The question becomes, how long before microplastics fully break down into individual molecules, or before these molecules themselves disappear? Because it takes much longer, but they do disappear eventually. Microplastics undergo physical fragmentation when they are exposed to UV light or movements in their environment, due to wind or waves, for example, as well as what is called chemical weathering. That is to say, they react chemically with oxygen, they oxide, or light, which is called photodegradation. They break into even smaller particles, smaller fragments, called nanoplastics, that are defined as smaller than 1 picometer. And they keep disappearing like this over hundreds or thousands of years. In practice, on our planet, microplastics have an estimated half-life of up to 2,500 years. Half-life, that is to say the time it takes for half a given sample, a given quantity, to fully break down and disappear. In practice, it means that if you spread 1 pound of microplastics on Earth, in average, half a pound will remain in 2,500 years. Of course, it depends on where they are. In the sea, more or less deep. It goes faster near the surface because there is light that triggers the breakdown. In cold, dark and low oxygen areas, like the deep sea or buried landfills, it tends to be more. Now, 2,500 years is a lot to the scale of our lives, and clearly almost all of the microplastics we are producing today will still be around during the lives of our children's children. That's an ethical and environmental issue. But on a geological scale, 2,500 years is close to nothing. In 1,000,000 years, there are 400 periods of 2,500 years. So if we take this half-life of 2,500 years as a basis, it is fair to say that only traces of the microplastics we have produced until now will remain in 1,000,000 years. In 2,000,000 years, everything will be gone and microplastics will have been cleaned up. So, returning to our initial question, the objects and fibers made of hydrocarbons, of plastics, that our civilization produces on a massive scale, will all have been entirely broken down in a couple million years. In other words, if a civilization had produced plastic bags, toys, or synthetic clothes more than 2 million years ago, we couldn't find them, let alone at the time of the actual Silurian period, 400 million years ago. Now, plastics may disappear, but what about metals? What about big and dense metallic objects like a military tank or the vessel of a nuclear reactor that are built to be particularly resistant? Metallic objects do not decompose like organic materials, they corrode. That is to say, they react with oxygen to form oxides or hydrogen to form hydroxides. Iron does it relatively fast. It rusts. But even steel, which is mostly a mix of carbon and iron, does it too, including stainless steel. All alloys that include small quantities of other elements, such as chromium. They are formulated to corrode much less. And they corrode much slower, indeed, but they do, eventually. Here again, corrosion highly depends on the environment, especially the presence of water or oxygen. But to give you an idea about orders of magnitude, objects like cans, metal chips, or beams used in construction would disaggregate in a few decades to a few centuries if they were no longer maintained. They would break down into smaller pieces of corroded metal that keeps reacting and could eventually turn to dust. A dust of iron oxide, mostly. The larger the surface exposed, the fastest it corrodes. So things like metal cans or sheets of metal would disappear first. But eventually, all iron-based objects on Earth would be affected. Stainless steel used in appliances, tools, or structures would take longer, but the order of magnitude is a few thousand years. This is important for our buildings, because they are essentially made of materials that can break quickly on a geological scale. Stone, brick, mortar, wood, and metal. If humankind was to disappear entirely, leaving its buildings behind, of course wood would disappear first, attacked by insects and decomposing, but more solid elements like brick and mortar would also collapse in a few decades to a few centuries, especially in regions where it rains a lot. A building that is not maintained will end up having infiltrations of rainwater, or humidity will accumulate in the walls, dissolving cement and bricks in a few centuries. And even different types of stone, be they sedimentary, like limestone, or magmatic, like granite. Magmatic means it comes from the cooling and solidification of magma or lava. For these it takes much longer, tens of thousands of years. But if they are exposed to the air or humidity, they would be affected. For many buildings, vegetation would also attack their structures. Roots are very strong. They can cause dislocation of foundations and walls when left unchecked. So, in a theoretical world where humankind would have disappeared overnight and would no longer maintain any building, most houses would collapse in a few decades or centuries. The first skyscrapers would collapse in a matter of decades too, due to infiltration and the corrosion of their metal structures. And after a few thousand years, there would barely be a single building still up. Again, that would depend a lot on where they are very dry regions with little to no seismic activity would offer better conditions. For example, there are Egyptian monuments, starting with the pyramids, that are thousands of years old and they still stand. But even there, erosion due to the wind and the very slow but real reaction of stone to the moisture in the air, however dry the air may be, would make them disappear eventually. After a few tens of thousands of years, all buildings ever built by humans would have turned to piles of rubble and would be in the process of breaking down into ever smaller particles. There's the question of whether they could survive longer if they were buried by sedimentation, or why not fossilize? We will discuss that later. But any building on the surface would be affected by this decay and would start a process of disappearing. Now, staying with metals or alloys, what about metals that are not as reactive as iron and its alloys like steel? For example, aluminium or noble metals like gold that do not oxide at all. Aluminium that is used in cans, foils, or aircrafts is very resistant to corrosion. Still, it does oxide. It is resistant because it typically forms an oxide layer that prevents further oxidation. This means it happens more slowly, but it still happens. Aluminium foil would disappear or break down into tiny particles in a few centuries. Larger and thicker objects would last thousands of years. Still, not that much for geological times. The same is true of copper, bronze and brass, these two last ones being alloys containing copper, tin and zinc. They also form a protective layer that protects them and slows down oxidation. But it happens, and actually bronze objects that date from a few thousand years, like swords or figurines, are generally found already very altered. Another class of metals is the ones that do not react at all with oxygen, noble metals, such as gold or titanium. In their case, it is true that they will not naturally disappear or break down. There are parts of electronic devices or jewelry that could stay absolutely unchanged for hundreds of millions of years, billions of years even, and be found as new, as long as they are not destroyed. For example, molten under the earth's crust or buried so deeply that they cannot be detected. Now, if we try and imagine what product or what waste left by an industrial civilization lasts for the longest period of time, another thing that may come to mind is nuclear waste. When we speak of nuclear waste, this covers very different things. The least problematic type of waste with the shortest lifespan is equipment, materials that served in nuclear plants and have been contaminated, from machines to things like gloves and clothing. These need to be handled carefully, but given that they are just contaminated objects that are covered with radioactive particles, rather than actual radioactive material, they quickly lose their radioactivity in a matter of years. It never entirely disappears, but it converges with natural radioactivity, this low level of radiation that exists on our planet everywhere, because we are surrounded with a few unstable atoms that eventually decay and emit radiations and tiny particles. These equipments lose their radioactivity quickly and then break down, like the materials we spoke about before, be they plastic or metal. What lasts much, much longer are some isotopes, some subproducts of the fission of the fuel, generally uranium, used in nuclear reactors. You know that when uranium atoms fission in a reactor, which is what we want, this is what releases the energy that powers a nuclear reactor and makes water boil. So when they fission, plenty of new atoms form, different isotopes. An isotope is a type of atom with more or less neutrons. What defines an atom is its number of protons in its nucleus. But most atoms have different possible variants, possible versions, with more or less neutrons. And this number of neutrons is a big factor that determines how stable they are. For example, the element carbon has 6 protons in its nucleus, but there can be more or less neutrons. Most common carbon atoms have also 6 neutrons. They are called carbon-12. 12 because of the 12 particles in their nucleus, 6 protons and 6 neutrons. But there can be more neutrons. You heard of carbon-14, for example, that serves for the dating of fossils or archaeological artifacts. Carbon-14 has 8 neutrons, and it is mildly radioactive, meaning that it is a bit unstable, and eventually carbon-14 atoms will decay into another element, in that case nitrogen. It is thanks to this property that carbon-14 is useful for dating. Because if you have a given sample of carbon-14, half of it will disappear due to radioactive decay in a period of precisely 5,730 years. It is the concept of half-life that I told you about before. Carbon-14 has a half-life of 5,730 years. So if we take, for example, a piece of prehistoric wood that formed in the past and contained a standard quantity of carbon-14, and we measure how much of this carbon-14 remains in it today, we can deduce how many half-lives took place since it formed, and from there estimate how old it is. Now, some of the isotopes, the new atoms that result from the fission of uranium and then the fission of other elements born from it because it goes on, some of the isotopes that appear when nuclear reactions take place in a reactor disappear very quickly. They have half-lives of a few seconds or minutes or hours. These disappear inside the nuclear reactors, also contributing to power them, as their fission releases more energy. But some other isotopes have very long half-lives, tens of thousands to millions of years. There are several of them with very long half-lives, but an extreme case is an isotope of iodine, iodine-129, with 129 particles in its nucleus. And this one has a half-life of 16 million years. So 16 million years after it is taken out of a nuclear reactor, half of it will still be there, continuing to decay and generating life-threatening levels of radiation. This is the long life or very long life type of waste that the nuclear industry generates. And even though processes exist to reduce this ultimate waste to the minimum, there are still tons of it produced each year around the world that need to be stored somewhere. In most countries, they are stored underground, in underground facilities. So this is a trace that we are leaving behind us, and even in 10 half-lives of iodine-129 in 160 million years, there will still be tons of it on Earth. Ideally, this ultimate waste should be taken to storage sites dug in geological formations that are expected to remain stable for millions of years, because they are well above sea level and far from the edges of tectonic plates. But this is often highly controversial because no one wants such a repository facility near them. For example, in the US, there is a proposed site, a project that has been around for decades to create such an underground depository in Nevada, the Yucca Mountain Nuclear Waste Repository. But it has faced enough opposition to be delayed multiple times and still hasn't received the type of long-life nuclear waste it was designed to store. But regardless of where we end up putting this nuclear waste, it is here to stay and will testify of our existence in tens of millions of years. But considering such long periods of time brings us to another set of questions of a more geological nature. The natural alteration of artifacts, or the radioactive decay of nuclear waste, is one thing, but it is something rather theoretical. In real conditions, the surface of the Earth evolves. There is plate tectonics, volcanism, why not big asteroids reaching the surface and causing cataclysms? There is sedimentation too, different mechanisms that may deeply bury or even destroy the traces of our existence. On the other hand, objects, or why not even human bodies, could also fossilize and be preserved for a very long time as mineral prints of what they used to be. So let's look into these aspects, starting with the question of fossilization. Could we leave fossilized traces that would last millions or hundreds of millions of years? Under the term fossil in paleontology, there are quite different types of remains. A fossil is defined as a preserved remain, or even an impression of any once living thing. The body of a prehistoric creature can become a fossil, but so can a print left by the foot of a dinosaur. So, more than a specific type of object, a fossil is a material piece of evidence of ancient life, including very small life forms. The oldest known fossils we have in the fossil record on Earth date back from more than 3 billion years, and they are microscopic microorganisms. So fossils can survive for extremely long periods of time, provided they are buried in places that protect them from erosion, because they are mineral items. The first process that causes fossilization is called replacement. It is when tissues are buried in a wet environment before they decompose, and the groundwater in this environment has to be rich in dissolved minerals like silica or calcite. This groundwater, over a long period of time, will seep into the pores and cells of the organism, depositing its minerals that replace all the biological material. A lot of shells were preserved this way. It is not really that the tissues or cells have turned to stone. They are replaced with stone, as these dissolved minerals take the space left by the biological material when it breaks down and is taken away. The result is a fossil that preserves the external shape with a new composition. A variant of this process that can happen in similar conditions is called permineralization. Here too, mineral-rich groundwater deposits minerals, but instead of replacing everything, the minerals form like a coating on a very fine level, including on a cellular level, which preserves the original organic structure. A lot of dinosaur bones or wood were preserved this way, and this gives some of the best fossils because it creates extremely fine molds of their cells. Yet another process is carbonization or compression. When an organic body is buried in a hot and low oxygen environment with pressure, volatile elements like carbon are going to escape from this buried organic matter. But because it is buried and pressurized, the carbon cannot escape further. So it forms a thin carbon film that outlines the shape of the organism. You have probably seen these 2D shapes or prints of ancient fish on rock, sedimentary rock. A lot of plants too, with the outline of their leaves and stem. These darker impressions are the outlines of organisms that underwent fossilization by carbonization. There are also rare cases of almost unaltered preservation. The best known example is entrapment in amber. Generally it is insects or fragments of plants that were trapped in tree resin that later hardened into amber. Inside this kind of sarcophagus without oxygen and the resin filling in every cavity, the organism is preserved as it is. Other mechanisms that can lead to unaltered preservation may include freezing in glaciers or falling into natural asphalt or tar traps. But in practice, these traps or frozen medium do not last for more than a few thousand or tens of thousands of years. So technically they may create fossils, but they will not have such a long lifespan before the glacier melts or the tar trap disappears due to movements underground. And also freezing slows down decomposing dramatically, but at the temperatures we have on Earth, it doesn't stop it entirely. So eventually the organism will decompose, even if it is frozen. There are other, rarer processes, but one last type of fossils are the remains that are indirect proofs of life. such as molds and casts of footprints, or of feces, what is called coprolites, that are fossilized feces. Here too, these molds and casts are due to minerals filling a cavity and drying as the water that carried them evaporates or trickles down further into the ground. These casts are rougher than replacement or permineralized fossils, because here, instead of having a fine coating or replacement on a microscopic scale, it is just minerals fitting an underground cavity left by a decomposed organism or a trace of its activity. So are mineral fossils eternal? In theory, pretty much, as long as they are buried into a stable and dry geological layer, where erosion, due to wind or water, cannot reach them. Still, fossils are rare, and only a tiny fraction of living organisms ever fossilize. Because it takes extraordinary circumstances such as a landslide that suddenly buries them entirely, be it on land or underwater, or a drop of tree resin big enough and liquid enough to trap them entirely. It also takes a medium with perfect conditions of protection and mineral-rich groundwater. A human body could perfectly fossilize, and the proof is that we have fossilized bones and skulls of prehistoric men. But the condition for these fossils to keep existing and be discovered later is the stability of their medium and its accessibility. If they surface, they will be destroyed by erosion, and if the geological layer in which they are trapped goes under a tectonic plate and dives back to the Earth's mantle, they will also be destroyed. If they are buried under miles and miles of sediments, they will become unretrievable. So this brings us to the geological question: how does sedimentation work? And how long do geological layers survive before the surface of Earth is refreshed with new material coming from volcanoes or the rifts between tectonic plates that move away from one another? Sedimentation is the geological process by which sediments, solid particles, accumulate as layers on the Earth's surface. These particles may be carried by water, such as in riverbeds or at the bottom of the seas and oceans, or by air under the form of dust. These sediments are produced by the erosion of rocks due to water or wind, or they can be biological remains, for example the exoskeletons of tiny crustaceans underwater, or even on land. Or they can be produced by chemical precipitation, when two fluid elements, liquid or gas, react and form a solid. So they are of different origins, and over time they form an ever-growing layer of accumulated sediments that, given time and the rising pressure, may turn into new rocks, sedimentary rocks. At the scale of our lives, it is a slow process, but one that is still perfectly perceptible in some places. Just think about this thin layer of dust that accumulates in our homes if the furniture is not regularly dusted. In a few days, it may become visible. After a few weeks, it is already rather consistent. And if you give it 1 or 2 years, the layer of dust can be relatively thick, like around 1 millimeter, depending on how air circulates inside a home and the quantity of particles in the air. But take this millimeter of yearly dust and multiply it by 1,000 for a millennium or 100,000. It becomes feet above feet of piled particles. And 100,000 years is not much, geologically speaking. Another quick tangent, by the way. What is the dust in our homes made of? It depends on where you live and the air outside your home. But it is always a mix of different things that will make you want to vacuum your home more often. From the inside of the home come tiny fragments of textiles, clothing, carpets, curtains. There's also dead skin cells, hair, and dust mite debris. From outside, every time we open a door or a window, enters outdoor soil, pollen, bacteria, mold, spores of plants and fungi, tiny bits of plastic, these micro and nanoplastics we talked about before. All of this floats in the air and eventually settles on every surface. Now, geologically, what happens in our homes is anecdotal. Bear in mind that the phenomenon also happens in oceans that cover 2/3 of our planet. In the oceans, there is a constant rain of mineral and organic particles, what is called marine snow, on which many organisms feed all the way down to the oceanic floor. Part of it ends up piling down at the bottom. Under most seas worldwide, except near the rifts where new oceanic floor is being created with magma coming from the Earth's mantle, in other places the layers of sediments can be several kilometers or several miles thick. So sedimentation tends to slowly bury everything in most places on Earth. And it happens slowly but surely, all the time and almost everywhere. Technically, the rare zones that are spared sedimentation are places where humans remove sediments, in our cities, our villages, our homes, or the top of mountain chains that provide sediments due to wind and water trickling down as rain, snow or glaciers, but they barely receive any sediments. Now, when geologists speak of sedimentation, what they have in mind is essentially underwater sedimentation, in riverbeds and even more in the seas, where the phenomenon creates enormous layers over time. A lot of continental regions on Earth are called sedimentary plains. These land areas were submerged long ago, and then, either because the plate they were on went up, or the sea level went down, they became emerged. Typically they have kilometers or hundreds of meters of sediments that tend to form large plains, often fertile plains. In America, the eastern United States, particularly the Atlantic and Gulf coasts, and the Midwest, are vast sedimentary plains. So is a large part of Europe and the northern half of France, for example. Sedimentary plains are very common, and people living on them are used to find little fossils of shells, not specifically on beaches. It can be everywhere, in forests, in fields, in gardens. These are all small marine creatures that lived millions or tens of millions of years ago, and they fell down to the bottom of the ocean to stay there in the sedimentary layer until they emerged and ended up on land. So, at what speed does sedimentation take place in oceans? In the abyss, far from every coast, and where the water column may be several miles high, it is rather slow, around 3 millimeters per 1,000 years. That is to say, in a million years, if nothing affects the process, only 3 meters of sediments will accumulate. It is so slow because sediments brought by rivers or the erosion of the coastline don't reach these regions. Closer to the shores, and if there are waters with a lot of marine life, it goes much faster. In open seas or oceans that are a few hundred meters deep only, it is around 1 centimeter per 1,000 years, so 100 meters per million years. And on continental shelves and coastal regions, it can be several centimeters per year. With a lot of mineral sediments carried away by the rivers that end up falling and staying on the seafloor a few miles from the coast. Sedimentation is the fastest in estuaries and deltas for the same reason. It can be several centimeters per year when rivers carry a lot of sediments, like the Amazon or the Mississippi or the Yellow River in China. Over long periods of time, sedimentation happens almost everywhere. As the sea level rises or tectonic plates go slightly down, or due to airborne sediments that can be carried even between continents. For example, the Amazonian region receives sand from the Sahara in Africa, carried by winds. So almost everything can end up buried under meters and meters of sediments. It can help preserve remains. For a large part, we owe our understanding of the different geological periods of Earth and the history of life on our planet, or the history of its climate, to sedimentary layers. But in the long run, it also makes everything disappear. It will hide the remains of any civilization so deep underground that they can become undetectable. Undetectable in many places, at least, not exactly everywhere at the scale of a planet. We still have access to layers that formed hundreds of millions of years ago. So, returning to our question of detecting the remains of a very ancient industrial civilization, given everything we talked about before, it seems reasonable to assume that some of its most resistant artifacts, such as parts of electronic devices using noble metals or jewelry, or fossilized elements, including bodies and body parts, could theoretically survive in sedimentary layers and be retrieved millions or hundreds of millions of years later. But that takes us to another question. How long do continents survive? What about their complete destruction when they undergo subduction under a tectonic plate or due to erosion? How fast is that on a planet like Earth that is geologically active? Here we have to distinguish oceanic crust, which is about 60% of Earth's surface, and continental crust, which is 40%. Oceanic crust refreshes, that is to say, it is recycled and fully replaced relatively fast. The oldest zones of oceanic crust on Earth are only 280 million years old. You remember the Silurian period was more than 400 million years ago. So nothing remains of the oceanic floor that existed back then. And everything on it was destroyed. The edges of oceanic plates are subdued, meaning they go under other plates and they melt as they dive back into the Earth's mantle. Why do they dive like that? Because they are pushed by other plates or by rifts, these zones where fresh magma rises and forms a new oceanic floor. In oceanic rifts, like north to south under the middle of the Atlantic Ocean. This Atlantic rift is what pushes apart North and South America on one side and Eurasia and Africa on the other side. So the Atlantic Ocean expands. And one day, in tens of millions of years, it will become larger than the Pacific Ocean. So, in average, the renewal timescale for this oceanic crust is around 200 million years. Every 200 million years, pretty much all the oceanic crust on Earth has been refreshed. On continents, it is much slower. There is a bit of lava spreading here and there around volcanoes. But at the scale of continents, this is not much. It is almost negligible. Most of the destruction of continents comes from subduction and erosion. Subduction is less pronounced than for oceans, and it is logical. Continents are on plates that are thicker, higher, and oceanic plates tend to go under them. So in some cases, there is a bit of subduction. There are also rifts that open on continents too, like in Eastern Africa, or one day, in a very, very distant future, there could be another one opening in California. This is less certain because the situation on the coast of California is with two plates sliding rather than drifting away from one another. But after millions of years of sliding, a rift could open there. As the sliding continues, in around 20 million years, Los Angeles and San Francisco should become adjacent. That's an example of partial destruction of continental mass. And south of them, in Mexico, Lower California has already been pulled away from the Mexican mainland, forming a big peninsula. So continents are affected by subduction and the opening of rifts, just much less than oceanic floors. And then there is erosion that tends to flatten out continents in the very long term. So continents also get destroyed, but it is way slower than the bottom of the oceans, and as a result, the continental crust on Earth is much older on average. Its average age is estimated to 2 billion years. And that's why we had access to fossils that are so ancient. The full reworking of the continents is estimated between 1 and 2 billion years. That's a lot of time, but it doesn't mean that coastlines are always stable, they move. Due to the variation of sea level, And in the long term, this variation can be significant. At times, like in the Cretaceous, 100 million years ago, the sea was 200 to 250 meters higher than today. That's around 700 feet higher. So between the variations in the sea level, the rise of certain parts of the continent where mountains go up while other areas go down, much of today's land already existed 400 million years ago, but was submerged at times. And vice versa. Areas that were part of the landmass are now underwater. Estimates about how much of today's emerged land was underwater at some point during the past 400 million years range from 50 to 80%. And that tells us that in the long run, a lot can disappear, but there are also spots on Earth that have been emerged for hundreds of millions of years, often far away from the edges of tectonic plates. And in these regions of the planet, the fossil record has been preserved. So such places exist. Fossils could still be accessible there in a very long time, and given that humankind occupies large regions of Earth, we would probably leave traces in some of these zones 100, 200, 300 million years from now, even if they are under a thick layer of sediments. We would leave probably faint traces, because as we have discussed, only a small fraction of what we build could persist and testify of our existence. And this limited material trace that we would leave is an important argument for the authors of the Silurian Hypothesis, given that little can remain of this direct evidence of our industrial civilization after a few hundreds of thousands of years, and after millions of years barely anything detectable. They thought that a better approach may well be to look for indirect evidence, signatures of the existence of a lost industrial civilization. What could these signatures, these markers be on a planet? They could be of different types. First, traces of nuclear activity. We discussed the waste left by civilian nuclear reactors, and I told you about examples like iodine-129, one of these very long-life subproducts of nuclear fission. But if we also include nuclear weapons, there is even longer than that, like plutonium-244, that has a half-life of 80 million years. Iodine-129 was only 16 million years. So nuclear events, such as a bomb detonating, and also the waste from reactors, can leave a radioactive trail, a signature, from isotopes that do not occur naturally or not in such quantity. And these can last a very, very long time. Another signature indicating an ancient industrial civilization could be an impact on life in general, biological markers. Humanity today has a massive and very fast negative impact on biodiversity, since we started to industrialize at least, and that was only 200 years ago. It was yesterday. The estimated decline at the moment in the number of species is considered by most experts as largely outpacing any extinction event in the history of Earth. And this quick decline, this mass extinction that is happening at the moment, this will leave traces in animal species and in the fossil record of our period. Mass extinctions may have different explanations. It can be volcanism, dramatic climate shift, asteroids. But at least based on how our industrial societies work and their impact on living species, a particularly sudden and fast mass extinction in the absence of other factors could be evidence of the existence of an industrial and advanced species on a planet. And still, by studying geological layers, this industrial activity can also leave other traces there in sediments. Less vegetation due to deforestation, acidification of oceans, highest concentrations of metals that were extracted and spread on the planet, or impacts on the atmosphere that also leave markers in sediments. For example, a rise in carbon dioxide due to the extensive use of fossil fuels, of hydrocarbons, or nitrogen from fertilizers. This being said, this signature would not necessarily be easy to read. For example, 56 million years ago, at the end of the Paleocene period, there was an extinction event with a rapid warming of the Earth. A warming thought to have been caused by a spike in volcanic activity and releases of methane into the atmosphere. This left a signature in the geological record with quickly rising rates of carbon dioxide and acidification of oceans, a signature that could easily look like the product of an industry that burns fossil fuels. But still, our societies are currently leaving traces in the geological record that will stay in place for hundreds of millions of years, and maybe will provide proof of our existence to another species in a lot of time, a terrestrial or extraterrestrial species that would reach Earth. I told you at the beginning that all these questions had connections with astrobiology, that is to say, the search for the possible existence of life in space, in any other place than Earth, and the detection of extraterrestrial civilizations on faraway planets. Why is that? It has to do with the Fermi paradox that I told you about in previous episodes. The Fermi paradox is the observation that we never came into contact or detected any other life form, let alone an intelligent life form. And this sounds paradoxical, because theoretically there should be plenty of life in the universe. Life may have very small odds of appearing on a given planet, but however small the chance, there are so many planets, billions of billions, across billions of galaxies, that there has to be life somewhere else, and in so many worlds, that millions of intelligent, advanced, and why not industrialized civilizations should theoretically exist. So where is everybody? Why are we alone? There are various possible explanations to this paradox. It could be that the likelihood of life appearing has been overestimated. It could be that we are too far apart, and it would be materially impossible to communicate regardless of technology. The distances would be just too great. Or maybe extraterrestrials already found us and they observe us like a zoo. We just don't know it. Or yet another one is that intelligent life forms always self-destroy after a relatively short period of time. Maybe just a few hundreds or thousands of years after they begin industrialization. And that would be the blink of an eye in cosmic time. These advanced civilizations would go extinct before making contact, and that would explain the Fermi paradox. Yes, millions of advanced civilizations could well exist across the universe, or rather have existed, but just for such a short time that they are condemned to remain alone. They appear at different periods and for too little time. And this is why astrobiology may find interesting to define tools, approaches, clues to detect extinct industrial civilizations. Knowing what we should look for would be very useful to find evidence of these possible extinct civilizations. Maybe there was one on Mars or on Venus in the very far past of the solar system. It looks very unlikely, but it cannot be entirely ruled out. So this thought experiment can also be productive this way. And beyond these aspects, the Silurian hypothesis is also a mirror we put in front of ourselves. An invitation to reflect on how we alter the planet. Maybe not really because we are at risk of destroying life on our planet. The Earth survived many mass extinctions and radical changes over the past 100 million years. We are probably not going to destroy life. It is in too many places and too adaptable to not rebound eventually. But for our own sake, it invites us to think that civilizations are not eternal. So it reframes humanity's place in time, and it prompts questions about our legacy and our stewardship of the environment. We have reached the end of our story for tonight. If you are not sleepy yet, please pick another story in my library. You can embark on another journey, another adventure. Or, if you feel sleepy, keep your eyes shut and let yourself go. I'll be back soon with a new story, and in the meantime, sleep well. Sweet dreams. Au revoir.